Okay, so here is part 2, delta G, E, and K, and the Nernst. And the first part video, you pretty much you'll know how to do the problem, number 1, the older problem that I linked. And then the new one, using these equations is what I'm going to do right now. And there might be a part 3 I'm going to see. I might do 2 problems like this for you. I'll show you, or at least I'll set up, because I wanted to show you something a little bit different about one problem that's coming. Okay. I know I dropped my eraser and I had to use this old cloth here. Where is that eraser? Oh well. Okay, so we found the cell and we found the E of the cell, 1.61 volts. Now, it's important also, well, it will be important to see the overall cell reaction. I guess I didn't need to erase the whole thing there, but oh well. Well, I just want you to see and know that this is zinc plus 2, and this is Mg plus 2 solution here. That's going to matter for the Nernst coming up. There's a salt bridge. Okay, all right, here we go. So the first question, it says on letter C, we did A and B. Calculate the value of the standard free energy change, delta G, for the spontaneous cell reaction. The words they're going to probably use now in the AP are calculate delta G for the thermodynamically favorable cell reaction. What is the thermodynamically favorable? It is this one right here, the one you see there that we got in the very beginning when you looked at your 2 equations, you flipped one and you made sure you get a positive number. That is the thermodynamically favorable reaction right here. So what is delta G for that reaction? All right. Well, there's an equation that relates delta G negative N times the Faraday constant times the cell potential. Now, what is the Faraday constant? I'm going to talk more about this on another, but 1 Faraday is 96,485. They actually updated that number. Coulombs per mole. Now, a coulomb is the unit of electrical charge. So imagine how much, if you walk across the floor on carpet and you touch a piece of metal and it shocks you, think about that as receiving like a coulomb shock. That is not a coulomb. What you're getting is, I think I looked this up somewhere, it's like it's 1/50,000th or 1/100,000th of a coulomb. That's what that is. 1/100,000. No, 2. It's 2/100,000. So that means 10th, 100,000, 10,000, 10th, 100,000, 10,000, 100,000. Right there will be there. That's how much of a coulomb shock you get when you walk across the floor, or in your car, you slide across the seat and then you touch the door and it shocks you. You're getting about that much of a coulomb. So 1 coulomb is 1 coulomb is kind of like the standard unit of charge, 1. So that tells you what if that's the shock you get from the carpet or from the door, what's going to happen when you get like 100 coulomb or 96,000 coulombs. You don't even want to think about that shock. But it's that many coulombs for every mole of electrons. And a mole of electrons, how many electrons is that? 6.022 10 to the 23rd. For every 1 mole of electrons, if you want, you can put a 1 if you want to, but for every 1 mole of electrons, that is how much charge that you receive when it is transferred from one side to another. You know what? That's one question I did not do on the last video. Is it going clockwise or counterclockwise? And remember, all you got to do is look at the equations. Zinc is gaining the electrons. Magnesium is releasing the electrons. So since magnesium releases, it's going that way. So this time, yeah, it is going clockwise. I guess it was last time as well. Magnesium sends out the electrons to that way, and then they come back over, and then they come back. The charge comes back through to the other side. So, the zinc ions receive the electron, the negative charge there. So, all right. So what I want to do the math. Okay, so here we go. The Faraday, I'm going to just plug it in. So to calculate and it should be the standard, again, whatever they put, if I put standard is NF, E standard, well, non-standard will be E non-standard. And there's something really important I'm going to tell you about this at the end of this problem. But I think I'll tell you right now. Okay, the spontaneous will this reaction that we have set up, will it occur spontaneously, or is it thermodynamically favorable that will occur? Yes, it is, because E of the cell is positive 1.61. So if the cell potential, if the voltage is positive for the whole cell, it is favorable, thermodynamically favorable. The reaction will occur spontaneously. If it were negative, it would not occur spontaneously. There's a way to make it occur, but it would not be spontaneous. Okay, I'll have to get to that later on. Now, delta G is just the opposite, and you remember that from thermo. If delta G is negative, it's spontaneous. That means it is thermodynamically favorable. It will occur. If delta G is positive, that means it is not spontaneous in that direction forward. It will be not thermodynamically favorable. Okay, so look, here is what does it. E has to be positive to be favorable, to be spontaneous. Thermodynamically favorable. E is positive. So in the equation there's a negative sign, and so you see that that's positive. G will be negative. If that were negative, then G will be positive. So it makes sense. So just remember that's one little statement in the essay. Well, I don't want to say essay, but a short answer that you might need. Okay, N represents the number of moles of electrons transferred from one electrode to the other electrode. Okay? And in this one, how many moles of electrons are transferred? You have to look at your balanced equation, and you see that in the balanced equation, 2 moles of electrons, 2. So 2 go from magnesium, they leave, and 2 come into the zinc. Now, this reaction, what I should have done, if this had not been if they were not equal, just say that there had been a 1 there, okay? Well, I would have to multiply all this by 2, but not the number. We remember that. I would multiply the whole thing by 2. But it would be 2 moles of electrons transferred for that number. So that will equal the number when the electrons equations are balanced to cancel out, and it was 2 and 2. Then that is the number you use. So negative 2. Well, I'll just put 2 moles of electrons. Moles of electrons times the Faraday constant, 96,485 coulombs per mole of electrons. As you see, that's going to cancel out with moles, electrons, mole electrons. Now you multiply times the voltage, the cell potential. Now here's how you do this. A volt can be converted into what's called 1 volt. You need to remember this number and know that 1 volt is equal to 1 joule per coulomb. Okay? 1 joule per coulomb. 1 volt equals 1 joule per coulomb. 1 volt is equal to 1 joule per coulomb. So if it's 1.61 volts, it's 1.61 joules per coulomb. Think about joule as energy and work, and like a punch to it. Like, okay, boom. Joule is like the energy you see there. Every coulomb gives you that many joules in this particular cell. But different cells, if you have zinc magnesium battery, if you have a lithium battery, if you had a battery that was silver and magnesium, all of them have different voltages. So as far as electrons going from one place to another, it depends on what chemicals you have, what metals you're using to get the actual voltage. Some have a bigger punch than others do. You know, those lithium ions batteries are amazing. They're really, really strong, last long. So some have a bigger punch than others. So think about that. The voltage of a cell is going to depend on what metals you use. But so the number of joules you get per coulomb. The coulombs are not all the same. I mean, you can send a coulomb from one place to another. 10 coulombs in this battery are not as forceful as 10 coulombs in like a lithium battery. Okay? But anyway, here we go. Get the answer. I'm talking too much about it. So 2 times 96,485, 1.61. So let's do that. 96485 times 1.61 times 2. It's negative 311,000 joules. Watch your unit. Joules. Okay. So that's your, that would tell you that this reaction would go as written forward. it would be spontaneous forward, thermodynamically favorable forward. Okay. All right. 296.588. Wait, did I do something wrong? Oh, no. I did it right. Okay. All right, now, next question. It says, determine the value of the equilibrium constant KEQ for the cell. Okay. Now, this is something, delta G equals negative 311,000 joules. I'm going to remember that because I'm going to erase this and show you this. Okay, there used to be an old equation they gave you on the AP. They don't give it to you anymore. I'll show it to you real quick. It's the log of the equilibrium constant K is equal to N times the cell potential divided by a constant 0.0591 in a standard 592 in a standard cell. They don't give you that equation anymore. Don't worry, you don't have to worry about it because instead they give you this equation. Delta G is negative RT ln K. All right, I'll put a little degree by those as well. Okay, so what I'm going to do is I'm going to use that equation. Delta G is equal to negative RT ln K. Now, I'm going to put in the value. Let me check my R values too. It's going to be 8.31 for your R value, and it's under thermo. You're going to find the R value is under the gas law constant. Yeah, joule mole Kelvin. I think they just did this to make it a little bit easier to have less equations for you. But remember, you could set these two things equal to each other. Negative NFE equals negative RT ln K. So why in the world are we talking about equilibrium anyway? All right, let me show you that and bring that up right here. What happens is this equation can be considered an equilibrium system. But you never want a battery to reach equilibrium because if it does, that means the forward and the backward are going at the same rate, and you'll have no more cell potential. It'll be zero. Your battery will be dead when you get to equilibrium. That'll happen. But you can also go backwards, and when you run this reaction backwards, you're actually charging the battery. You charge it, then it goes forward. All right, then it goes forward, it slows down, gets near equilibrium. Then he goes backwards, you charge it back up again, and so forth. So this is an equilibrium system. First, let me just show you, because it's going to come in a little bit later, what's the equilibrium constant for that? Well, how would I write the constant expression for this? Well, look at this reaction. This is a solid. We don't put solids. Zinc is a solid, but I have magnesium ion and to the first power, and zinc also to the first power. That makes it pretty easy. So there's your K expression, the magnesium concentration or the zinc concentration. So yes, you can consider it an equilibrium problem. So I'll show you that right here. And what I'm going to do is just plug them in. For R, it's going to be 8.31 joules per mole Kelvin. Don't forget your negative sign. The temperature, it said, was 25 Celsius, right? Yeah, it's going to be standard. And remember, it must be in Kelvin. 298 Kelvin. All right. And also, yes, I have many things going on at one time here. And then your constant, ln K, will go right there. Okay, so here we go. Let's get the math of this. So 8.31 times 298. Oh, and I didn't put my G value, which I had to put in, negative 311,000. Negative 311,000 joules. Okay, so the joules will cancel out. So I'm going to take 311 divided by 311,000 divided by 8.31 divided by 298. And that gives me a positive 125.5. So I'll put 126. Now, don't worry. On these answers, you're going to see on my paper I might have done it. You might get an answer far off from what I got. But think more about what the exponent power is, and hopefully you'll get that same exponent power in this thing. So one more time, double checking. 311,000 divided by 8.31 and divided by 298. 126 equals ln K. Now remember what you do. E raised to 126 is e to the ln k. That gets rid of the k. So k equals e to the 126 power. I'm just going to keep the calculator number here and see. Looks like I get 3.5 times 10 to the 54 power. Okay? All right, so, or if I put in 126, second, then ln. Now I get 5.26, 10 to the 54 power. So it's very different depending on the numbers you put. But I'm going to put the first one I told you, 3.5, 10 to the 54 power. Don't worry. If you put 125, you're going to get a drastically different number here, but you will get the 54 power right. So that will be your equilibrium constant for this cell reaction. All right. And then the last little bit, the last question is about the Nernst equation. And here's a quick, easy way to tell you what in the world is the Nernst. We'll look at it and it will make sense. E of the cell equals E of the cell degree minus RT in Faraday constant L in Q. Well, guess what? If you have a standard cell, that means this is 1 molar and that's 1 molar, then you don't need to use a Nernst equation. The Nernst is for a cell that is not standard. And notice that here it's not standard, here it is. So you take the standard value, which we found 1.61 volt, and what's going to happen is you're going to either increase or decrease the potential of the cell based on the molarities. This is a neat thing that can be used to manipulate a battery. You can increase the molarity or decrease the molarity in 1 or 2 cells, and it will affect the voltage. So you can raise the voltage or lower the voltage based on that. Pretty neat. And look at this. Do you remember Q? You know what K is? Well, Q is like the weather condition, the weather status, weather report for Q for that. So here's what it says in number letter E. It says another cell is constructed identically except the concentration of zinc is 2 molar and magnesium is 0.750 molar. Determine the value in volts of the cell potential. So remember the K expression. Well, first of all, let's look at that. The K expression is going to be the magnesium ion molarity divided by the zinc molarity. Now, since there are it's a 1-to-1, 1-1 ratio, it's easy. If you ever had a squared or whatever, make sure you watch out for those numbers. They change. So if magnesium is 0.750 and 2.0 for zinc, that becomes Q. Q is 0.750 over that. So here's your K expression. Q is the same thing. You just plug in the numbers. Are you at equilibrium? Remember we talked about that. Well, you don't ever want to be at equilibrium in a cell because there'll be a 0 voltage at that point. But anyway, 0.750 over 2.0 is equal to 0.375. Or 0.38 really. Is it really 2.0? It is 2.0. So it would be 0.38. 0.38 is Q. So watch what's going to happen here. Now, here's a little bit of a math knowledge prediction thing. You know, if I take the log of like 100, you know the log of 100 is 2. 10 to the second power, 10 squared is equal to 100. So it's a positive number. It's a number greater than 1, right? The log of 100 is greater than 1. The log of 1 is 0, okay? But the log of, just to say, 0.1 is going to be -1, okay? So log of 0.1 is -1. Make sure I'm telling you right. Sometimes I like to check my calculator. Yeah. All right. Well, here's the point they want you to see. If this number in here is greater than 1, then your log will be a positive number. And if it's a positive number, look at what's going to happen. If this is a positive number, then it's going to make the cell potential get lower. You're going to subtract it. That's all you need to know. Minus, forget all that. Minus a positive number here. These are all positive. Minus a positive number, it's going to go down. If the log of this number, if this number is less than 1, like 0.1, it's going to be a negative number and it's going to increase the potential. You can actually do that like on a multiple choice question without having to do any math by knowing this, okay? Well, that's just a little shortcut, but let's just do the math. You can always do the math as well. The same thing is true for log and for natural log, by the way. I mean, they're not the same numbers, but the natural log of 1 is also 0. The natural log of a number greater than 1 is positive. Natural log of a number less than 1, like 0.999 or 0.001, they're going to be negative. Okay? Well, here we go. So let's go back to this. So the E of the cell will be the 1.61 volts that we already got minus, let me find a way to plug all this stuff in. We're going to have to use 0.38. So log of Q, the natural log of Q is a natural log of, I'll just have to plug this in here to save space, but I'm going to erase this here. So we already see that that number is less than 1. So that means it's going to be a negative number. Negative times a negative is positive. It's going to cause an increase in cell potential. But anyway, you can predict that. R is 8.31 joules mole Kelvin. Okay. T, it's standard. Is it standard temperature? It should be. Yeah, 298 Kelvin. We'll assume it's 298 Kelvin. They didn't tell us, but it has to be. They would tell you otherwise because the problem before it was. I'll keep the mole Kelvin down here, but the number of moles transferred were 2 moles of electrons. That's when they're balanced out, 2 moles. And the Faraday is 96,485 coulombs per mole of electrons times the natural log of this. And let's find the natural log of, so negative, this minus that, what a lot of math this is. 0.38 natural log is negative 0.97. Okay, so, wow, I got to multiply all of this. Let me brackify all that just to make it a little bit easier. That's times 0.97, by the way, not minus. Okay, so 8.31 times 298 divided by 2 divided by 96,485 times 0.97. It looks like it's negative times a negative. So 1.61 minus negative 0.012. Okay? So what will that be? 1.61 minus a negative is plus. 1.61 plus 0.012 is 0.012 plus 1.61 is 1.62. So the voltage, the new non-standard voltage is it went up from 1.61 volt to 1.62. All of that work just to go up a little bit. But hey, you got 0.01 of a volt up. Okay, so you should now be able to do the problem that I gave you. I think I might show you one more problem just so you know how to do it. But you're good with doing the homework now, the other Nernst equation problem. And I might say more about it later because most likely the Nernst can also come up as like an essay question, as I was telling you before. And usually the secret to that is just knowing what happens to the Q. If I increase that or decrease that or decrease that or increase that or, or both or whatever, what happens to the cell potential? And you can, a lot of times you can figure that out. But you usually want to know, will it increase or will it decrease? All right, I will see you guys later on.